Welcome to this presentation in 5 parts, how to solve a set of linear simultaneous equations. The reason I'm doing this is because I used to keep repeating myself to both undergraduate and postgraduate students, so I decided to put it all down in just one document. It's at the level of last 2 years of school, for some of it at the beginning, then for undergraduate university level, and then finally for postgraduate level. It's aimed at students who are studying engineering, but also computer science or physics, or any science that's got a strong numerical element or data processing element. Finally, there are no bells or whistles in this. It's simply trying to get you to understand all the aspects of solving linear simultaneous equations from first principles and giving you hopefully useful visualizations and a good basic understanding of what the problem entails. So why am I doing this? Well, it's because that linear algebra and certainly the least squares problems of ax equals b, and that's related to what's called regression, is probably the most important mathematical concept in machine learning. Lots of different applications. I've just labeled a few of them here, which I suppose are some of the most well known. Massive MIMO and 6G systems, deep learning, spectral analysis, compressive sensing for MRI, etc. Loads of applications where you might need this. And finally, the important thing is that deriving these results from first principles gives a very helpful understanding, and it also gives you a visualization into the maths behind the applications above and the nature of the problem. Now, if you want to skip straight to one of the main results, you can do so. You might find everything else a bit boring and say this is all you want to know. So here we are. Don't let this put off people who don't know anything about least squares or linear algebra. It'll all be explained. This really is saying that the solution is given as the pseudo-inverse of the matrix A, where ax equals b, and when A is full rank, it simplifies to these expressions. That's just one of the results, but in case you want to just cut to the chase and leave now, go ahead. For those of you who want to stay, let's look at the contents. So we're going to do in section 1 a very quick first example. We're then going to look at ax equals b and the least squares problem. We look at some visualizations of the problem, which really helps you get a better understanding. We look at solving ax equals b with weights and constraints, and then give 2 final examples. I'm just scratching the surface here, but as I say, the whole idea is to just give you a sort of basic understanding of the problem and some of the nomenclature. But this is just 1% of the tip of the iceberg. So a quick first example is probably the best way. So let's take a look at some data here. Let's say we've got unemployment versus time, and these time instances are all non-equally spaced, so they could be completely and utterly irregular. And what we want to do is we want to look at a trend. And if we think the trend is a straight line, we say let's fit a straight line to those data points. And how do we do that? Well, we could say there's the equation of a straight line, and we want to find the best estimate for m and c, so that line will fit, inverted commas, these points in the best possible way. And that's probably the most basic and most familiar least squares problem. And students at school study this under regression analysis. I know, I've checked. So this is at school level. So let's start by fitting a straight line to the data. So what we do is we draw a line and we take any point, say ti, and we say what's the difference between the predicted value and the actual measured value, and we call that the prediction error. So we can write the prediction error as this for all of the n points. So if we draw or write down that equation explicitly for n points, we get this. And then we can say, okay, what are the values of m and c that minimize the sum of the squares of the error? And we'll explain why we do that later on. So we're trying to minimize the energy in the error. And that's the criterion that we've decided to go by. There are other ways that you could do this. You could minimize a different function, but this is least squares. Okay, so we write down the sum of all the error terms squared, becomes that. And if we want to find the minimum of that with respect to m and c, we just partially differentiate the objective function, set equal to 0, and we get the very famous normal equations. So it's just a bit messy, it's not difficult. You end up getting these equations, 2 equations and 2 unknowns, m and c. You can easily solve that yourself, and if you do, you end up getting this expression here. So there's the values for m and c, and if you put those values in, you get the optimum gradient and the optimum intercept to give you a least squares solution and best fit a straight line to that data. Well, a much more elegant way to deal with this is to use what's called linear algebra. So we start with the equations that we had over leaf, and we write them like this and stack them into matrices and vectors. So we end up getting this expression. The column vector of the error is equal to A, which includes the time information, and multiplied by X, which are the two unknowns, minus B. And we want to solve that. So we want to solve the energy of the errors. And we can do that by writing E transpose times E. You all know that will give you the sum of the elements squared. And if you write it like that and expand it and then differentiate with respect to the vector X, you get this expression here, which is the least squares solution. We'll come on to this later on, so don't worry about not understanding this yet. If you now plug in the value for A there, you'll see that you get exactly the same equation that you had before. But from now on, we'll continue to use vectors and matrices. Now, we said that the trend was a straight line. It may not be a straight line. Perhaps it's some sort of polynomial. And so then we'd use a higher order polynomial like this. So we're using an mth order polynomial in T. And we have m plus 1 unknowns. That's A0, A1, A2 up to AM. And so we do exactly the same thing as we did before. We write down the error equations, which is the difference between the predicted value of the polynomial and the actual value. And we end up getting this expression here. So A, the matrix A, instead of becoming just 2 columns, it's now become m plus 1 columns. And the unknowns, we have m plus 1 unknowns. So again, we get exactly the same solution, except the only difference is the A's and the B's are now different. But if we change the order of the polynomial, it's very easy to change A and to change B. Now, one of the problems with this is, what do you choose for M? You must have some rough idea of what the underlying trend is, but if you don't choose it correctly, you can either underfit or overfit, and overfitting is a problem, as we'll see later in machine learning. So what we've got here is an example of where we take some data and we try to fit it with a straight line. We get this. Clearly this is wrong, and this is underfitting. If we say choose a polynomial of order 10, we get quite a good fit, and we can see intuitively that that probably is tracking the trend. If we go too high, then what we get is overfitting. So if we increase the order of our polynomial, it will then be possible, because of the extra degrees of freedom, to draw a line that almost goes through every single point. And the problem that we've got there is we're trying to find the correct value for m, and it's quite a challenge. And the problem, as I say, is that what you have is noise and the model. And what we've done here is we've probably captured most of the model and just a little bit of the noise. What we've captured here is the noise plus the model, which is what we don't want. So that's overfitting. Okay, that's the end of that short part 1. We're now on to section 2. It's called AX equals B and least squares, and I'll see you there.